In our video yesterday, we took a look at how we could solve equations with exponents by getting a common base and setting the exponents equal. We also concluded by saying that we can't always get a common base. Sometimes we need a different strategy, and to set up that different strategy is what we're going to do today. And then tomorrow, we'll look at how we can use this different strategy in order to solve exponential equations with different bases. But first we have to understand what logarithms are and their properties and how we can use them. So to start off with, we're going to look at the definition of exactly what a logarithm is. A log is an exponent. Simply put, it's how we solve for the exponent. If we've got some type of base raised to some exponent that is equal to some type of answer, we can rewrite this problem, exactly the same problem, using what's called a log. We will put a subscript of the base and we will stick the answer in there. And it will always be equal to the exponent, because a log is an exponent. The log will equal whatever the exponent is. So for example, if 7 squared equals 49, then we could rewrite this as a log with a base of 7 of 49 would be equal to that exponent of 2. Both of these are expressing the same information, but one is solved for the exponent. The exponent 2 is equal to log base 7 of 49. The other one is solved for the solution. 49 is equal to 7 squared. But each form has its advantages. We can also switch back the other way. I could tell you that log base 5 of 7 equals a. And you could rewrite this as an exponent problem because 5 is the base. The exponent is what the log equals. A is equal to 7. The most essential thing you should be able to do and understand is how to switch back and forth between log notation and exponent notation. Because sometimes a problem is easy in log notation and hard in exponent notation. Or sometimes it's easy in exponent notation and hard in log notation. So when we hit a brick wall in one form or the other, we'll switch to the other form, because generally the other form will always be easier. So let's first look at how we can evaluate a log. If I want to know what log base 6 of 216 equals, the way we're going to evaluate logs is we are going to rewrite as, actually no, better said, first we're going to make it equal to x, and then change to an exponent. In other words, if we want to know what log base 6 of 216 equals, for now we're going to say it's equal to x. And whenever we get our solution for x, that must be what log base 6 of 216 is. So first we will rewrite it as an exponent. 6 to the x power is equal to 216. Well, the nice part about 216 is we know that's 6 to the third power. And so we've got the same base on each side, and as we've seen before, we just set the exponents equal. So x is equal to 3, or log base 6 of 216 is equal to 3. We can even take a look at what is log base 2 of log base 5 of 25. Well, first starting inside parentheses, because that's what order of operations tells us to do, log base 25 of 25 we make that equal to x. And when we change this to an exponent, we have 5 to the x equals 25. And 25 we know is 5 squared. And so the exponents must be equal, x must equal 2. Which means that all this stuff in the parentheses must equal 2. Which means log base 2 of log base 5 of 25 is really saying log base 2 of the answer we just found of 2. So maybe we should say log base 2 of 2 equals x, and do it again. The base of 2 to the x equals 2. Well, g, make those exponents equal to 1, equal to each other, x equals 1. So log base 2 of log base 5 of 25 must equal 1. We can even do this with some ugly looking things, but the process should still be the same. If we have log base the square root of 3 of 1 over 27, we want to know what that equals. So for now, we'll make it equal to x. Rewrite it as an exponent. We have the square root of 3 to the x equals 1 over 27. And we can get both of these to have the same base because square root is really just a 1/2 power. So we have 3 to the 1/2 x, and 27 is 3 to the 3rd. We make it a fraction by making it a negative third. Then we can take our exponents and make them equal to each other. 1/2 x equals negative 3. And solve by multiplying both sides by 2, and x equals negative 6. So log base square root of 3 of 1/27 is equal to negative 6. Similar to how we evaluate logs is how we solve a simple log equation. And that is, we're going to convert to an exponent problem. The way we're going to solve these is we're going to convert to exponents. So let's take a look at an example. Let's do log base 4 of x equals 3. Can't solve it as a log, so let's change it to an exponent problem. 4 is the base, 3 is the exponent, equals x. Well, 4 to the 3rd, that's easy, that's just 64, equals x, and we solved the log equation. It's pretty much the process we're going to go through to solve these simple log problems. If we have log base 2 of 3x plus 5 equals 4, can't solve it as a log, so we'll change it to an exponent problem. 2 is the base, 4 is the exponent, equal to the 3x plus 5. And then we just solve from here. 2 to the 4th is 16, equal to 3x plus 5. Subtract 5, and we have 11 equals 3x. And divide by 3, x is 11 thirds. It's pretty simple to solve these log equations. Again, the most important thing you can do with logs is convert between logs and exponents and logs. You should be able to do that without hesitation, without any doubt in your mind about how it's done. More interesting to us, though, in this college level class is how we do the properties of logarithms to help us do some more advanced things. The first 4 properties we're going to see if we can figure out intuitively. So the first one is going to be the log base anything of 1. What's that going to equal? Well, let's think about it over to the side here. If we said the log base anything of 1 and made that equal to x, we'd be saying a to the x equals 1. What exponent will always give us an answer of 1? Anything to the 0 power is always equal to 1. So the log of 1 will always be equal to the exponent of 0. That's our first property you should know. The other one we should know is the log of base anything of anything. What does that equal? Well, if we think about that, we're saying log base anything of anything, we'll make that equal to x. And so we'll say that anything to the x is equal to anything. If we make that exponent 1, we see that x is equal to 1. When the base of the log is the same as the base of the problem, they're inverse operations, essentially. They undo each other, leaving just the 1 behind. Which kind of leads to log base a anything of that same thing to the x power. Essentially, we're saying log base anything of a to the x is equal to some unknown x. Well, if we rewrite this with a as the base and x as the exponent, a to the x equals a to the x. The exponents must be equal. This just equals x. Because the base of the exponent and the base of the logs are the same, the solution is just going to be the exponent. And one we don't see very often, but it works much the same way as if we have a base with a log base a of x. Again, the base of the exponent and the base of the log are the same, so we're just left with the guts of x. So these are the 4 basic primary properties that you should know about logs. The next 3 are not as intuitive, but they kind of make sense when we play with them. So let's play with them. We're going to play first, and then I'll tell you what the answer is after we're done playing. We're going to say, let's say u is equal to a to the r power. And w is equal to a to the s power. So if we were to change these into logs, the first one would be log base a of u equals the exponent r. And the second one would be log base a of w equals, I don't like doing s. Let's not do s. Let's do t. A to the t. That way it doesn't look like a 5. So as we play, we're going to look at what happens when we multiply u times w. Now, u times w is essentially saying a to the r times a to the t. And what we know about exponents is we can add exponents r plus t together. So u times w is equal to a to the r plus t. Let's rewrite this as an exponent, as a logarithm property. If we wrote this as a log, the base you see is a, and uw is what's inside the log, and it will equal the exponent r plus t. And here's the rub. The important conclusion is r is log base a of u. plus t is log base a of w. Which means log base a of u w is equal to log base a of u plus the log base a of w. This is our important fifth property. What this property is essentially saying is if we're multiplying two things inside the log, u times w, are multiplied inside the log, it can be rewritten as a sum of two logs. And that makes sense, because we know that if we multiply two bases, we add the exponents. And the logs are the two exponents being added together. We can do a real similar exercise. We'll call this number 6. Again, with our plane, we're saying u equals a to the r. We're saying that w equals a to the t, which means if we change these into logs again, it would be log base a of u equals r, and log base a of w would equal t. But this time, instead of multiplying u times w, I'm going to divide u divided by w. Which means we're really taking a to the r divided by a to the t. And again, our exponent properties then tell us that we should subtract those exponents. So that's a to the r minus t. And then if we convert this to a log again, the base is a of u over w. It's going to equal the exponent r minus t. But again, we know that r is log base a of u. And t is log base a of w. So we get this new property that log base a of u over w is equal to the log of u plus the log of w. In other words, if we're dividing two things inside a log, whoops, big mistake there. It was a minus in the problem. It should still be a minus. There we go. Minus, minus, minus. It was r minus t. If we're dividing two things inside a log, it's the same as subtracting two individual logs. Which makes sense if you think about it on several levels. With exponents, we know if we're dividing two bases, we subtract the exponents. Logs are exponents. So dividing two pieces means we subtract the two pieces in individual logs. Another thing that makes sense is a negative log, the second piece, a negative log, you could think about as a negative exponents. And where do negative exponents end up? On the bottom of a fraction. So this property just makes sense all around when you think about it in terms of the fact that a log is an exponent. Negative exponents go on the bottom. Division, we subtract exponents. It just all works. Here's one more. This one we're just going to do a single u is equal to a to the r power. And we're going to rewrite this as a log base a of u equals the exponent of r. Did I mention we're doing a lot of changing between logs and exponents and logs? Did I mention that that's the most important thing you can do after this lesson? Okay, good. So here, I'm going to start with u, and I'm going to raise it to a constant, u to the c power. Doesn't matter, some exponent. Well, that means I'm really taking a to the r and raising it to some exponent. We have an exponent property that says we can multiply those two parts together, those two exponents. We really have a to the cr. I'm just going to put it alphabetically. So if we rewrite this as a log, we want to make the base a. So log base a of the other side, which would be u to the c, must be equal to the exponent on our base, which is cr. So you can see if we rewrote this, it would be a to the cr equals u to the c. We could have written it another way with a base of u, but we've been kind of on this theme of base a, so I want to stick with this base a theme. What's nice about this is r, we remember, is equal to log base a of u. And so this gives us log base a of u to the c is equal to c times log base a of u. And this becomes our seventh important property. And the important property, what we're often going to see it called, is we're going to grab that exponent inside the log and move it out front. Exponents inside the log can move out front as multiplication. And that makes sense, because if we have an exponent inside of an exponent, because a log is an exponent, we multiply those together. So multiply the exponent times the log times the other exponent. Something we can never do, though. I see this all the time on test. Someone's going to do this on our test. Don't let this be you. Someone will say the log of a plus or minus b, it doesn't matter, and they will say, hey, I got an idea. Let's distribute the log. They say log of a plus or minus, depending on the sign, log of b, because they distribute the log. That does not work. How do I stress this enough? You cannot do that. Cannot do that. First off, the idea of distributing the log does not work, because log is an operation. It's not times log. Log is an operation. That's like distributing plus, or distributing square root, or distributing cube, which people do all the time. That's bad too. Log is an operation. You can't distribute it. We're not saying log times a plus b. We're saying the log of a plus b. It's function notation is what it really is. It's saying f of a plus b, where the log is the function. Do not distribute the log. There is no such property. I make a big deal about it now. Someone's going to do it on the homework. Someone's going to do it in class. And someone's going to do it on the test. Don't do it. Log cannot distribute. Okay. Off my soapbox. Let's do some examples where we can use these properties. We're going to write as a single log. One advantage of these properties is if we have a lot of logs that are added and subtracted together, we can squish them together into a single logarithm that's easier to work with. For example, if we've got log base 2 of a plus log base 2 of b minus log base 2 of c. We can squish these three logs using our properties into a single logarithm. First, we'll write it as a log base 2. They all have to be base 2. And then inside the log, one thing I like to think about is positive logs are positive exponents. They're going to end up in the numerator. Negative logs are negative exponents. They're going to end up in the denominator. So the a and the b are positive. Added together, they get multiplied in the numerator. The c is a negative log, and so that's going to end up in the denominator. We can compact log a plus log b minus log c together into log of a times b divided by c. We can add an extra step to this and say, how about 4 log base 7 of a minus 2 log base 7 of c plus 5 log base 7 of d minus 1/2 log base 7 of x. First, before we squish all these together into a single log, we've got all these coefficients out front that are going to make life difficult to work with. But we have a property that says those coefficients out front can double as exponents inside. So this is the same as log base 7 of a to the 4th minus log base 7 of c squared plus log base 7 of d to the 5th minus log base 7 of x to the 1/2. And in fact, that 1/2 is better expressed as a square root. 1/2 power, remember, the index is the denominator of the fraction. Now we can write these all as a single log base 7, where positive exponents are multiplied in the numerator and negative exponents are multiplied in the denominator. So we have a positive a to the 4th, a negative c squared, a positive d to the 5th, and a negative square root of the x. Might be tempted to rationalize that denominator, but I'm going to let you be lazy on this problem today, and we will stop there at log base 7 of a to the 4th, d to the 5th, over c squared square root of x. We've squished this down and combined it to a single logarithm. We can go the other way too. We can expand logs and write them out as many, many, many logs. In fact, in actual application, this is the way that you prefer to go usually. And I'll show you some examples of this, where we take one log and we stretch it out into many logs that are easier to work with, or that we know stuff about. So for example, if we have log base 5 of a squared b cubed over cd, we could expand this out so that each factor gets its own log. So we're going to do a log base 5 of the a squared plus, because it's positive, it's in the middle, numerator, log base 5 of b cubed. The c and d are in the denominator. They're negative exponents, so they're negative logs. Negative log base 5 of c, negative log base 5 of d. And we can complete this expanding process by grabbing those exponents and moving them out front. Grabbing those exponents and moving them out front. Actually, this process of grabbing an exponent and moving it out front is going to be essential for what we're doing tomorrow. We've got 2 log base 5 of a plus 3 log base 5 of b minus log base 5 of c minus log base 5 of d. And we have our expanded logarithm. Let's do one more example where we're expanding. Let's expand log base 3 of 9a square root of b over c cubed d. Again, each factor gets its own logs. Positive logs mean numerators. Negative logs, like negative exponents, mean denominators. So going across the top, we have a log base 3 of 9. Plus, still in the numerator, a log base 3 of a. Plus, a log base 3 of the square root of b. And I'm going to change that to an exponent, b to the 1/2. Because as you might have guessed, we're going to play with exponents in a minute. The c cubed d is in the numerator, so we're going to subtract log base 3 of c cubed, and subtract, because it's still in the denominator, log base 3 of d. One more piece I want to play with is that 9. If we were to factor the 9, that would be 3 squared. Which is interesting because this now, log base 3 of 3 squared, is one of our properties that we saw at the very beginning of our properties discussion. Number 3, if the base matches the base, the answer's the exponent. So log base 3 of 3 squared, the answer is the exponent of 2. Plus, we can't do anything with log base 3 of a. Plus, we can grab that 1/2 exponent and move it out front. 1/2 log base 3 of b. Minus, we can grab that 3 exponent and move it out front. 3 log base 3 of c minus log base 3 of d. And in this way, we're allowed to expand our exponents. Why on earth would you want to expand your exponents like this? Well, let's take a travel down memory lane back to the dark ages before things like Google and text messaging and Instagram. Back to the days where we were asked to find logarithms by hand. There were no calculators that would calculate logarithms for us. You might notice your calculator has a log button on it. We're going to talk about how to use that button tomorrow. For today, though, we're going to talk about how they used to do it. And they used to have these books just full of tables called log tables. And these log tables would tell us the approximate value of various logs. It might say the log of some base, we're going to call our base a, of 2 equals 0.45. It would say that the log of this same base of 3 equals 0.72. It would say the log of this same base of 5 equals 0.97. And what you notice I've done is I skipped the number 4. In fact, I also skipped a lot of fractions and decimals. What the tables would give us is only the logs of the prime numbers. And then we would have to use the prime numbers by hand in order to calculate these other log values. For example, if we want to know what the log base a of 18 was equal to, we would say, well, 18, let's factor it. That's 2 times 9. Well, 9 is 3 times 3. So really, log base a of 18 is log base a of 2 times 3 squared. So let's take this multiplication problem and let's expand it. Let's write a log for each individual factor. We can do a log base a of 2 plus the log base a of 3 squared. In fact, we would continue simplifying by grabbing that squared and moving it out front. So we have log base a of 2 plus 2 log base a of 3. And now we're able to calculate what this equals. Because we know the log of 2 is 0.45. Plus 2 times, we know the log of 3 is 0.72. So the log of 18 is 0.45 plus 2 times 0.72, which is 1.89. We've now calculated what the log of 18 is. And we can use this pattern on any type of logarithm. We can even do it, let's do log base a of a fraction. How about 10/3? Well, that would be the log base a of 10 is 2 times 5 over 3. And so we would rewrite this as an expanded logarithm. We'll do a log for the 2, plus the log for the 5, minus, because it's in the denominator, denominators are negative exponents, log base a of 3. And I'm running out of space on my board. But we see that log base a of 2 is equal to 0.45. Plus log base a of 5 is 0.97. Minus log base a of 3 is 0.72. And so 0.45 plus 0.97 minus 0.72 is 0.7. So off my screen, it equals 0.7. We now have our solution. The log of 10/3 is 0.7. Let's do one last example of these. You should have those written down in your notes. I'm not going to keep scrolling up and down. Log 2 is 0.45, log 3 is 0.72, log 5 is 0.97. We're going to find log base a of 8, a to the 5th. Again, we need to rewrite that 8 in its prime factorization form, because it's the prime numbers that are going to be in our table. 8 is 2 cubed times a to the 5th. And so when we write this as 2 logs, we'll write it as log base a of 2 to the 3rd plus log base a of a to the 5th. Well, we know the 3 can move out front. So we have 3 log base a of 2 plus, we should also know that log base a of a to the 5th is 5, because the base of the log matches the base of the problem, so the solution is the exponent. And so the only substitution that really needs to be made is the log of 2. And we wrote down that the log of 2 is 0.45 plus 5. And so to get our answer, we do 3 times 0.45 plus 5. We get 6.35. And so in this way, we're able to find out a solution for these various logs that are not in our log table. And that's how we used to calculate them, before calculators. Today, however, we have calculators, and life's a little bit easier. But it can't be super easy. It would take far too much work to program your calculator to do every type of log possible. Log base 1, log base 2, log base 3, log base 4, log base 5. It would take a lot of time and energy. So we have a solution. We only put 2 logs on your calculator. We'll talk about the 2 logs in class or during the video tomorrow for the 4.3 section. But for now, we're going to talk about how we can take any log and change the base to match the base that we want. So tomorrow, we're going to want the base our calculator can do. For now, we'll talk about how we can change any base. And to set this up, we're going to consider some base to an exponent equals an answer. There's 2 ways that we can play with this. One way is going to set up what we're going to see tomorrow. The other way we've seen already. The way we've seen already over here on the right is we just change it to a log problem. We say the log base b of a equals the exponent x. But what if instead we had done something completely and entirely different? What if we had taken the log base c of both sides, a different base, a new base, the log base c of b to the x equals the log base c of a? Because I can do anything to both sides of the equation, and it's still equal, right? So, grab that exponent and pull it out front. X equals log base c of b, which is equal to log base c of a. Get x alone by dividing both sides by log base c of b. And x is equal to log base c of a over log base c of b. Here's where we get our formula. Notice originally we said x was equal to log base b of a, but after our plane we said it was also equal to log base c of a divided by log base c of b. So when we combine that together, we get log base b of a is equal to the log of a different base of a divided by log base c of b. This is our final property. It should have probably been included in our property list earlier, but it just fits into the discussion better here. We can change from base b to base c by dividing what's inside the log by the base of the overall log in two separate logs. So in other words, if we wanted to write log base 5 of 73 with a base 10, we'll say 2 base 10, we would say log base 10 of the 73 of the inside stuff divided by log base 10 of the base, which is 5. And this now has the exact same value, but we've changed the base from base 5 to base 10. Let's do one more example where we see this happen. Let's take log base 2 of 36, and we're going to convert it to base 9, just for kicks. Well, we would now have a log base 9 of the answer, of the stuff inside, of the 36, and we would divide by log base 9 of the base of 2. And this would have the exact same value. So it changes the base on the log. So we've looked at a lot of things today, really going over the properties of logarithms. First thing you need to know is how to change a log and an exponent between each other. A base to an exponent equals a, or log base b of a equals the exponent. You need to know how to do that. Second, we said the log base anything of 1 is always 0, because anything to the 0 is 1. We said the log base anything of that is always equal to 1, and that really comes off of the fact that the exponent is 1. So more generally, the log base anything of anything to an exponent is equal to that exponent. Technically, we can switch this around and say anything to a log base anything of x is also equal to x. They're inverses. Logs and exponents are inverses. They undo each other, giving just the inside. After 5 comes 6. We said that the log base anything of a product is equal to the log of the first one plus the log of the second one. Similarly, the log base anything of a quotient is equal to the log of the first one minus the log of the second one. Or how I like to think about it is negative exponents go on the bottom, positive exponents on the top. And finally, the last property we saw was the log base a of b. We can change the base to any other base we want of the stuff divided by the log of the base. Those 8 properties are what we really look at working with, and today we want to be really good at these properties so we can start to manipulate the logs to actually do stuff with them. That stuff we want to do involves solving equations, involves setting up application problems. Lots of great stuff. So take a look at the assignment today, and we will see you in class tomorrow.